Hello everyone. In this video, we are going to walk through some practical implementations of the resampling methods that we discussed in the slides. We will be using R as usual, and we will walk through how to do the validation set approach, the cross-validation, and the bootstrap methods. So let's break down the script into part by part, and let's walk through all of that. So let's start by, as always, we start by clearing out our workspace and load some libraries that we need. So we are going to use the auto dataset from the ISLR2 package. This contains information about automobiles, including horsepower and miles per gallon. Next, we set the random seed. This is important for reproducibility. It ensures that we get the same random numbers each time we run the code. Now, this line over here, line number 20, we run this line of code to create our training set by randomly sampling 196 observations from our total of 392. This gives us a roughly 50-50 split between training and testing data. The train underscore indices variable contains the row numbers that will be used for training. And now we fit the model. It's a simple linear regression with horsepower to predict miles per gallon. But one thing to note over here, we are only fitting the model in the training data set. So this extra option that we are typing over here, subset equals train indices, this ensures that the regression is only run on the training data. We attach our data set using the attach command, which makes it easier for us to write out the names of the variables. And then we calculate the mean square error on the test data set for the linear model. Yes. So once we have, so this is the code. Let's break down this calculation. So the predict function over here, this generates prediction for all observations. The subsetting, the negative train indices, by using the negative sign, we are selecting only the test observations that are there not in the training data set. We take the difference, we square it up, we take the average, that is our mean square error. This gives our test error for the linear model. We will then repeat it for the quadratic and the cubic model. So in this model, our MSE is 26.84. So let's see how this differs when we increase the model complexity. We fit a quadratic model, and then we calculate the MSE, and we see that model complexity goes down. So a quadratic model is a better fit than a simple linear one. We fit a cubic one, it starts to go up a little. So MSE was highest when the model was linear. It dropped a lot. It dropped to 19.57 when we fitted a quadratic one, and then jumped up a little bit, 19.62 when we fitted a quadratic, like a cubic model. The poly function over here, it's a useful one. The poly function creates orthogonal polynomials. It's a fancy way of including higher order terms in your model. So when I type poly within parentheses horsepower times comma 3, I'm fitting a cubic model in horsepower. When the order of polynomial is 2, we are fitting a quadratic model. And you can tweak this code just by a little to include a higher order polynomials. And to try out a different split, I change the seed number. Okay, so my earlier seed number was 1. now it is 2, and I do the exact same exercise again, and now we see that we have a different MSE. Earlier this value was 26 point something, now it is 25.72. For quadratic, it is earlier it was 19 point something, now it was 20.43. For a cubic model, again, we see different values of MSEs. So this is this is why this is a problem, like a potential problem with the validation set approach. Depending on your seed number, you can get different values of MSEs, which makes your conclusions very unstable. Now let's move on to the leave one out cross validation, or LUCV. First, we fit a model using the GLM function instead of an LM. So LM stands for linear model, GLM stands for generalized linear model, where LM is a subset of that. We fit a model and we get the coefficients. For linear model, LM and GLM produces the exact same result. So it doesn't matter whether you're using the GLM function or the LM function. As long as you're fitting a linear model, you will always get the same result. But we use GLM function here because the cross-validation function that we will use works with a generalized linear setup. And for that, we need the boot library, which contains a cv.glm function that we need for the cross-validation. So we load the library. If you haven't installed it before, make sure you have installed it first. So now we perform a LUCV for the linear model. So glm underscore fits a linear model of mpg on horsepower, and we fit it across the whole data set. And then cv.glm extracts the cross-validation error. And then we display the errors using the cv underscore $delta. Now look at the numbers over here. When I write this code, I get two results, 24.23151 and 24.23114. Let me explain what the delta component contains. It returns two values, as you can see. The first value over here is the raw cross-validation estimate of prediction error, essentially the average of prediction errors across all folds. Delta 2 does the same thing, but it tweaks a little bit and does some form of bias-corrected version of the same estimate. This correction addresses a statistical issue where cross-validation can slightly underestimate the true prediction error because we're using fewer observations for training than we would for testing, like for the final model. For LUCV, these two values are pretty identical to each other, or because the bias is minimal over here because we are using almost the entire data for training. However, in k-fold CV with smaller k values, the bias correction can make noticeable differences. In practice, most analysts use delta 1. So they usually go with this one when comparing models, which is what we will do in our code as well. So what we will do is that next we will use a loop to fit polynomial models of degrees 1 through 10 and compute the LUCV error in each scenarios. So we begin by initializing a vector to store these cross-validation errors, and then we will loop through polynomials of degrees 1 to 10, and for each model in each iteration we will first fit the model, then we will get the cross-validation error and extract the first entry of the delta and store it in the cv underscore error matrix. As you can see, it will take some time. And there you go. So for the linear model, the CV error is 24.23, and it declines, and it continues to decline, reaches a minimum of somewhere around 18.83, and then it starts to go up. And this is what we see. This is kind of replicates a U-shaped test error function. So testing error initially declines, but only up to a certain point, and then it starts to climb up. Next up, we have codes for the cross-validation. We again set a different seed for reproducibility, and we will, the only difference between the previous line of code and this is here we are specifying the number of folds using the k function. So by specifying k equals 10, we are doing a k fold, like a 10-fold cross validation. And we get slightly different numbers over here. So code-wise, cross-validation, k-fold cross-validation, and LuCV, there isn't much difference. The only difference is in this line of code, in this section. And as you can also see that it also took much less time to run these codes because we only needed to fit 10 models instead of n models. And the results are often quite similar because k-fold CV tends to have lower variance in its error estimates. Next, we have the bootstrap. So the bootstrap section, I will show you how to estimate the sampling distribution of statistics. And we will start with a portfolio example. I will define a function alpha underscore fn to compute our alpha underscore fn to compute our statistic of interest, which is alpha. So I run this line of code. What the function does is that it takes a data, it takes an index, and it creates an x and a y vector, and it creates a statistic, this variance of y minus covariance of xy whole divided by variance of x plus variance of y minus 2 variance of 2 times covariance xy. And we will calculate this alpha for all observations 1 to 100. And what we get is this. We get this value 0.5758. And then to perform bootstrap, we will take this function and we will draw samples of 100 times with replacement, and then use the boot function to estimate the sampling distributions. And this is what we see. Here, what is happening over here is that the boot underscore fn returns the coefficients of a linear regression. The boot function calls this 1000 times with different bootstrap samples. The output includes the original estimate and the bootstrap standard errors, which we can compare with the standard errors from the summary function. So notice something, the standard error through bootstrap is a little different than the standard error we get simply by running the regression once. And then we do the same exercise using the auto data set. And boot function, we compute the coefficients for the original data set, and then we set the seed, keep drawing multiple samples of 392 observations, do the bootstrap, and then compare it with the original regression results. So this is the results from the ordinary non-parametric bootstrap, and we can compare these standard errors from the standard model, and again you can see that the standard errors are different. Notice one thing, bootstrap doesn't affect the estimates. It changes the standard errors. So that is what resampling methods are. The good thing about these codes is that you don't have to manually code them out. You can do that if you want, but R has libraries that has functions that does this job for you. All you need to do is understand what the code is and what it is supposed to do, so that you can be sure that it is doing exactly what you want it to do. That's all. So that's the video over here. I hope this was useful. Happy to answer any questions that you may have. Thank you.